Okay, so this is chapter 3. We kind of finished up with chapter 2, so we're getting to these chapter 3 things. So vectors and scalars. First of all, vectors, talked a little bit about that because remember, some of the things we've seen so far are vectors. Vectors are a magnitude and a direction, a how much and a direction. Some of the vector quantities we have seen so far: velocity, acceleration, and displacement. These are some we have seen so far. Some we're going to see in the near future: force and momentum. Remember, some things require direction. What direction am I accelerating makes a lot of difference. I mean, if I'm coming at the stop sign, it's going to make a lot of difference whether I hit the gas pedal or the brake pedal. So I'm accelerating. What velocity? Am I going northbound or southbound on 280? On my displacement, or how far I am from a starting point. Now, scalars are a magnitude only. It's only the how much part. Now, a vector is a scalar in a direction. So the magnitude part is a scalar. An example of that is speed. Speed is the scalar part of velocity. Scalar part of velocity. But some quantities are only expressed as a scalar. Things like time, temperature, and one that looks like a vector but is really a scalar: energy. Energy is a scalar, although it looks sometimes like a vector. And we do talk about, remember, vectors is that plus and minus direction. Now, although we do talk about plus and minus with energy, it has to do with adding and removing energy. Adding and removing energy, but it is a scalar function. Anyone need more time? What? Against the wind, so in this case I have a negative 20, positive 10, so 100 plus a negative 20 gives me my resultant of 80 kilometers per hour over the ground. Again, the speedometer is saying 100. Speedometer would say 100, but when he looks down on his little chart, it was only going 180. This was very important. Like during World War II, if you ever read stories of them, the guys who were navigating, it was very important that the navigator would have his landmarks and know where he's going, things like that. Which is also why it was very important to the U.S. because we dealt in World War II with pinpoint bombing. When we did our bombing missions in Europe and Japan, we bombed in the daylight because we wanted to make sure we were hitting military targets. This is also why the British who bombed at night, didn't always hit the right place. But the Brits didn't always care where they dropped their bombs during World War II. Mainly because the Germans beforehand had been not too careful about where they dropped their bombs. Germans killed a lot of civilians, so the British didn't have too much sympathy for bombs dropping on civilians at night. They kind of, as General Sherman said, war is hell, that sort of thing. So you have to be very careful where you go, even from the sideways. This is why if you ever watch a ferry boat, if you had a ferry boat going across the river, if I'm here and I want to go there, if I tried to sail straight across, am I going to end up at the other station? No, I'm going to end up down here somewhere, which is why the ship, if you ever watch the ship, it's almost pointed that way. It's kind of pointing in, saying that way, and it actually goes straight across. But he has to take into account that part. In fact, there's a term, we would call this crabbing. If you ever watch a crab, crabs walk sideways. We had to do that a lot at the academy when we were coming with our boats, because the academy's on a river. When we come into the dock, we'd have to take into account this. Also, winds would tend to blow us off, so we'd have to come in kind of at an angle to stay in the right spot in the river on that. And we need more time. Now, when components are added together, you get that resultant. Resultant. So, on that. So if I had a component in a component, I would get together with this resultant. This process can be reversed. A vector can be brought into its horizontal components on that. This is what we call resolution. We say we resolve the vector. And that was one of your vocabulary words. So resultant, you're putting vectors together. Resolution, or we resolve a vector, means putting it into its horizontal and vertical components. Vertical component, horizontal component. On that, why those two components? Well, it would have to, if I had a number of vectors, like that. I wanted to know what is the resultant vector of those three. It will be very tough because they're all kind of different directions. I can only add a vector if it's in the same plane. In other words, the previous slide, all of the vectors were vertical. I can't add things that are horizontal. I can't put angles together. In other words, I cannot add this one and that one together directly, which is why I break them into their components. So I have their horizontal and vertical components of each one. So I can add, if I added all the verticals together, I might get this. I get, there is the resultant vertical. I added all the verticals. I have all my horizontals together, and I get a resultant horizontal. I can then find the final resultant. So you can see resolution and the resultant, they work together. We resolve our vector, get the horizontal verticals, add them all up, and then go back and put them back together again, and I get my resultant at the end. It's a way to solve it. This is where trigonometry comes in. We aren't doing trigonometry. But this is where trigonometry comes into physics, is basically all this vector stuff, putting them together, taking them apart, and stuff like that. Okay? We do have some relationships we need to learn. And it's very important we start dealing with forces and like projectiles. It's like with velocity, vertical velocity and horizontal velocity. They do different things for a projectile. You throw the ball up like that. The vertical component has its job, the horizontal component has its job. And they combine to give that path right there. Okay. So, on that. So anybody need more time? So, we have two special relationships we are going to deal with. One is the 3, 4, 5 right triangle. You might recall from geometry that if you have any right triangle, this is a right triangle with a side of 3 and a side of 4, the hypotenuse is going to be a 5. And that comes from the Pythagorean theorem. 3 squared plus 4 squared, take the square root, and get a 5. We don't usually use triangles this way. We take the diagonal, which really is the hypotenuse of the triangle. The diagonal is that hypotenuse. So if I had a vector of 3 at a right angle to a vector of 4, I'm going to get a resultant of 5. Conversely, if I have a 5, say at a certain angle, I know that I'm going to get a 4 and a 3. Or if I have the complementary angle on the other side of that. So it's that relationship that leads you to that. And now, by the way, this can be multiples as well. 15, 20, 25. Right? They're all multiple. If you can divide the same number out of them, and they have that ratio of 3 to 4 to 5. There's that ratio, 3 to 4 to 5. Then this would be that number, but that ratio, 3 to 4 to 5. It's a right triangle. Any questions? So that's one. And you'll see this again when we get into forces. We have an exercise that deals with this and things like that. Any questions? We need more time. The other relationship is the isosceles right triangle. Now, by the Pythagorean theorem, if I have a side of 1, side of 1, my hypotenuse is going to be the square root of 2, about 1.4. But the beauty of this, if I had a side of, say, 7, and a side of 7, the hypotenuse would be 7 times the square root of 2. If I had a side of 10 and a side of 10, this would be 10 times the square root of 2. So whatever your side is, the resultant is just going to be that number times the square root of 2 for your answer. All right. Remember, these both come from the Pythagorean theorem on that. Any questions? Anyone need more time? So there is one way. So one way to resolve our vectors is to use trigonometry and the Pythagorean theorem and things like that. You know, the whole SOHCAHTOA thing. We don't got to really worry about that. Another way we can do is graphically. And that's where your concept builder 3.2 comes in. We're going to practice some of this graphically. So the first half is actually finding our resultants. So the top half there. So everybody should have their 3.2 out. That's part of your notes. 3.2 is the notes. Remember, the 2 chapter 3 concept builders are part of your notes. Shouldn't be putting away your notes because we still have other notes on the other part, but this is part of your notes for practice. Now, we call this the parallelogram method. If we're going to make parallelogram, now remember, squares, rectangles, they're all the same. Parallelogram just means opposite sides are the same length and the same and are parallel on that. They are quadrilaterals, four-sided figures. So to resolve or find resultants. Now the first thing we're going to do is find a resultant. So I have my 2 vectors, in this case a right angle, and I'm going to basically make a parallelogram out of it. In this case, since they are at a right angle, we made a rectangle. We draw in the diagonal, which is the resultant. It is the resultant on that. Even if they don't come in a right angle, again, we make a parallelogram. So there's our parallelogram. This side and that side are the same. That side and that side are the same. We draw the diagonal, and we get our parallelogram.
What you're doing now is on the sheet, right?
No, this is not on the sheets. This is practice. So what you guys are going to do is on this one, this is the top half, you guys are going to draw, using the parallelogram method, draw in your resultants. You may help each other at your table and work on that. Like I said, the first couple, it's pretty easy. We just make, it's a rectangle. There's our resultant. Our resultant. Our resultant. So they're all rectangles, so we find that diagonal like that. These, you have to have parallelograms. So you're basically making the opposite side parallel, parallel. We draw our diagonal. Parallel, parallel. We draw our diagonal. Diagonal. Like that, something like that. This one actually should be directly horizontal. Close here. Like that. All right, questions on that? Now, this is finding the resultant. Any questions? Now, these are going to go in your notes. We're not doing the backside today. We'll be doing the backside another time. So, the other part is to resolve. This is resolving. Now this is breaking up that vector into its components. This is a little easier because it's always rectangles. We always construct a rectangle around. So we're going to construct a rectangle. There's my horizontal. There's my vertical. We construct that rectangle. Like that. So you're always building a rectangle. Remember, the vector is the diagonal of the rectangle. So it's always a rectangle, which makes it a little easier. My rectangle. So horizontal and vertical components. like that. So this is resolving, and that's the bottom part. Okay, the bottom part. So everybody resolve those vectors on the bottom part, please. So if we look at this, we are building a rectangle around like this. So there's my horizontal, and there would be my vertical component. This is a lot easier. Just always a rectangle. Always a rectangle. Like that. Now they do get to a point where they're giving you less help. So like that one. So there's one, there's one. So that's hopefully what you got for those. Are there any questions about those? These are part of your notes. So right now, you want to actually just put your notes on the side because you're going to need them in a minute because we're going to start our motion exercise on that. Motion exercise.